Hello everyone, my name is Taha Sabit, and today I will tell you about our project, Optimization of a Solar Tree in Egypt using MATLAB and Simulink. We are a group of undergraduate students at Nile University. Recently, the interest in renewable energy has been increased, and one of the most important conference, which is COP27, has been held in our country, Egypt, last November. Our project is a solar tree. There are two pictures of solar PV systems. The first one on the left produce 5 kilowatt power and take a land area of 20 meters squared. On the other hand, the right picture is a solar tree which produces the same amount of power with much less area, which is 1 meter squared. And this is the main value of solar tree. Solar tree stands for tree generating renewable energy and electricity. Solar tree is a biomimicry of the ordinary tree, where the leaves in ordinary tree represent the PV modules in our model. And there are some applications of solar tree where a small area is provided. Our problem is an optimization problem between the shadow loss and the structure cost. And we did this optimization problem using a single objective genetic algorithm in which we obtain the orientation, which gives the maximum irradiance on solar panels. And the second part is a multi-objective genetic algorithm in which we need to minimize area projected of solar tree and the shading loss. We will start by the single objective genetic algorithm. The main objective of this algorithm is to maximize the irradiance on solar panel, and this is done by changing the tilt angle and the surface azimuth angle. And we calculate the irradiance on solar panel based on this equation. And we use this equation to calculate the incident angle and the azimuth angle, which are function of longitude angle, declination angle, and hour angle. The values of this angle actually changing every hour. And then the main objective function of our genetic algorithm is the summation of the total irradiance over the year. And we then choose the best 20 values of tilt angle and surface azimuth angle, which gives the maximum irradiance on solar panel. And here's our code. And this table represents the best values for angles, which gives the maximum irradiance. The second part is the multi-objective genetic algorithm, and here we need to minimize two things, which are the projected area and the shadow loss. And this is done by changing the position of solar panels. And here, the flow chart we use to get the intersection of the solar of panel 1 shadow and panel 2 to calculate the shaded area. And this is the equation used to calculate the area. And this is the remaining equations. And here we use this flow chart to calculate the projection of panel 1 on panel 2. And then we get the intersection point from which we calculate the shaded area. And this process is repeated for each 4 times for each coordinate. For the genetic algorithm, the population size is set to 200, and the maximum generation size was 20 because of the limited computation power. And at the end, we obtain the best 20 position, which gives us the minimum shadow loss and the minimum projected area. Here is our code, and this table shows the best results. And we choose the first row to be our best one, which give us a minimum power loss with a good projected area. Here is our Simulink model. The solar tree consists of 20 solar panels. We model the 20 solar panel on Simulink. And here it takes 2 inputs, the irradiance, which we get from the single objective genetic algorithm. And the second thing is the temperature, which is dependent on our place in Egypt. And then we obtain the voltage current curve, and the second one is the power curve. Here, the blue one is the maximum power generated by these panels, and the red one represents the maximum power with the shading loss. In conclusion, we obtain a design for solar trees that produce 9 kilowatt for Egypt Sheikh Zayed city and consist of 20 solar panels. And thanks for listening.